This is video number 3 for section 8.5 partial fractions. And here I'm going to do another basic example where we are going to have just linear factors, non-repeated. So the first thing that I'm going to do is I'm going to factor my denominator. I'm going to get rid of the antiderivative symbol for right now because I don't need it until the very last step. The factored version of this quadratic will be x minus 2 times x minus 1. So from there, I can write my partial fraction decomposition form. I'm going to have a over the first factor plus b over the second factor. Don't forget to set it equal to the original expression. It needs to be an equation. Okay, the reason that it needs to be an equation is because now I'm allowed to cancel the denominators from both sides. But first, I need to take a and multiply it by x minus 1. And then I need to take b and multiply it by x minus 2 to equal 5x minus 7. So mathematically, that's how I am canceling my denominators. So let me just show you this really quickly. So what I'm doing is I'm multiplying both sides of the equation, or in other words, every single term in the equation by that common denominator. So if I multiply the first term by that common denominator, you're going to see that this x minus 2 is going to cancel with this x minus 2, and I'm left with a times the factor of x minus 1. If I look at the second term and I do the same, here the x minus 1 factors are going to cancel, and I'm going to be left with b times the factor x minus 2. And then lastly, on the other side of the equation, the entire denominator, both factors cancel, and I'm just left with the 5x minus 7. So algebraically, that's how we basically get rid of the fractions in a rational equation. So I've written that out. Now I'm going to distribute to get rid of the parentheses. From here, what I want to do is I want to gather my like terms. So you can see here I don't have anything quadratic, but I do have 2 x terms and then 2 constant terms. And so what I can do is I can say that this linear x term, ax plus bx, has to equal 5x. So I can combine those together to get one equation. And then here's my constant expression, which has to equal negative 7. But since both sides in this linear term have x's, I'm going to factor out the x to get rid of it so that I can divide x from both sides and come up with one equation that just has a's and b's in it. A plus b equals 5. And then of course my constant terms don't have any x's in them. From here, I can write that system of equations. So a plus b equals 5. Negative a minus 2b equals negative 7. And this one actually works out really nicely because in terms of using the elimination method, these two terms are already set up to go to eliminate or to cancel each other out. And so if I just add my b's and I add my constants, I'm going to find out that b is positive 2. And then if I solve for a, I can plug 2 back in for b, and then I find out that a has to equal 3. Whoops. So a equals 3 and b equals 2. Now that I know what my partial fraction decomposition is based on my constants a and b, I can write them out. Oops, that was step 6 already, sorry. I'm on step 7. So step 7, I solved the system. Actually, according to my steps in video 2, this is 8. It doesn't really matter, you don't need to label your steps this way. But anyway, what I have is the antiderivative of 3 over x minus 2 dx plus the antiderivative of 2 over x minus 1 dx. And if I integrate each piece individually, I'm going to get 3 times the natural log of x minus 2 plus 2 times the natural log of x minus 1 plus c. And just like in the last example, I can combine these into x minus 2 to the 3rd power times x minus 1 squared, all inside of the natural log, and then plus c. So that should be my final answer here. Alright, we have a couple of other scenarios that we need to look at here. We need to look at what happens when we have repeated linear factors. So for example, if we factor our denominator and we get x minus a to the m times x minus b to the n, or in other words, we have a multiplicity of one of our factors that is greater than or equal to 2. Well, the only change that needs to be made is in step number 2. That's the only thing that changes. Everything else is going to be exactly the same. So if I have some numerator divided by some factor to a power, some multiplicity greater than or equal to 2, then the way that this must be written is that a has to be written over x minus r to the 1st power, and then I have to add b and put it over x minus r to the 2nd power, and continue that pattern until I get to a power of m. And I don't know how many that will take, so something over x minus r to the m. So that's the only thing that happens differently, is how you set up your fraction decomposition. You have to make sure to include each power possible of that denominator in its own separate fraction. So let me just show you an example. And I'm not going to go all the way through the example, since step number 2 is the only one that changes. Let's just look at writing that partial fraction decomposition out. So here's an example where I would want to use partial fractions to integrate. You can see that the denominator is already factored. And so the way that this should be written out is that you should have a over x plus b over x squared. Again, this is the one, this is the factor that is repeated. So in other words, this is like having x minus 5 over x times x times x plus 1. But notice that each of these has a different denominator because you're increasing the power of your denominator as you go until you get to the power that exists in the problem. So because this is x squared, I've got one term with a linear factor of x and then another with x squared, and I don't want to leave out my other factor either. So that's how you would rewrite this particular example, and then of course you'd keep going with all the remaining steps. Alright, so that's one change that can happen. Another change is that you might have irreducible quadratic factors. Irreducible meaning that there isn't a factor in the numerator that cancels with a factor in the denominator, or that perhaps you maybe can factor again if it's more reducible. So if it's irreducible, it doesn't factor any further. I find that this is best shown with an exact example. So let me give you one. Okay, so here we're integrating this rational expression with a quadratic numerator and actually a cubic denominator that's been factored for us. So this factor right here is the one that we want to focus on. So this factor, first of all, doesn't factor more. And I say that because sometimes you might have x squared minus 1, which you could factor into x plus 1, x minus 1. So if it's a difference of two squares, then it factors more. If it's a sum, then it doesn't. So this particular one does not factor more. It is quadratic within itself. So that qualifies it as an irreducible quadratic factor. And so what we do to handle this situation, we take care of the linear factor just like we would. But with a quadratic factor in the denominator, the numerator needs to have a linear and a constant term. Okay. So if we have a quadratic factor in the denominator, then we need to express the numerator as a linear expression rather than just a constant. So basically your denominator has one more degree than your numerator. Numerator is constant, denominator is linear. Numerator is linear, denominator is quadratic. Okay, so if you have a quadratic factor, you just need to make sure that its numerator is represented by something linear. Okay, so those are some of the ideas that can happen here. And let me see if I can do one more example with you.